Yay!
Yay! Here's a neat little problem that will come in handy later. If you think about a hydrogen atom is, we said, you got a little proton, and then we had a little electron. Goodness, it's not a square, is it? Well, we don't know that, I suppose. Anyway, we had a little electron out here. So this is our electron, and this is our proton, right? Something like that. Okay, so the electron is just sort of whirling around. The classic kind of what we'd call the Bohr model is that it's moving around in like a circular orbit. So if it's a charge moving around in a little circular orbit, isn't that forming a little current loop? Couldn't I imagine that that is like a little wire with a charge going through it? So what is, let's see if we can compute, what is the effective current of an orbiting electron? So let's see what that would be. Well, the first thing we need to know is how fast it's moving around. And we've already figured that out, maybe like twice. Anyway, here was the idea. I'll do it faster this time. What's holding the electron in place? It's the electric force between the proton and electron. And if I write down that force, it's going to be K Q1 times Q2. Well, they're both the same charge E over the distance squared, R squared. Here's my R. That's like the radius of the hydrogen atom. Okay, there's my force. So this equals the mass of the thing that's orbiting, the mass of the electron, V squared over R, because it's in circular motion, right? That's the centripetal acceleration. So that means that my speed, the speed of the electron must be KE squared over mR if you cancel stuff out. Okay, so there's my V. And if you plug those numbers in, I think we've done this before, you get something like 2.2 times 10 to the 6th meters per second. Okay, so that's how fast this thing is going around. That's kind of mind-blowing, right? That it's this teeny tiny little atom, and this electron is moving at 2 million meters per second. So that's kind of insane. In fact, how long does it take the electron to go around once? One complete loop. Well, one complete loop. So we're going to try to find the period t of the electron going around once. So here's how we do it. This is kind of a standard thing you do. Is it's just the distance divided by the time is the distance divided by the speed. Right? Distance divided by speed is going to get you time. So the distance, how far around does it go? It goes 2 pi r. And then what's its speed? Speed is v. We just found that. So if you plug this stuff in, by the way, this r is like 5.3 times 10 to the minus 11th meters. Okay, so you plug this in, and I get, because this is the boring part, is doing calculator work, 1.5 times 10 to the minus 16 seconds. So that's how long it takes for the electron to go around once. Is this tiny, tiny little fraction of time, 10,000th of a trillionth of a second. Okay, well now we can get the current, right? Because current is just an amount of charge divided by some amount of time. Well, what's the charge? The charge is just E. And how long does it take to go around? We just found that out. That was our period. So if you take the charge and divide it by the period that we just found, what you get is a really cool number, about 1 milliamp. That's sort of amazing. It's amazing that it comes out to be such a almost like a real world number. It's like a current that you would find in, if you're trying to light up an LED or something. A milliamp is a kind of an everyday kind of a current. So one electron moving around a proton in a hydrogen atom has a current of about a milliamp. It's a little current loop of about a milliamp. That's kind of cool. We will use that. It turns out that that's going to be important for now what might be mysterious reasons when we talk about magnetic fields. But when we talk about magnetic fields and magnets, we will definitely come back and revisit this.